So let's talk about transforming our apps with Agentic AI. So I thought it might be useful to talk about the difference between AI agents and Agentic AI. The easiest way to think about AI agents are that they're task-driven. So they're predefined workflows to success or to getting an answer. In Agentic AI systems, they are more abstract, where you have a predefined goal, but the process for getting to that goal is autonomous, meaning the process is turned over to the AI system or the LLMs involved. Probably one of the most important points is that this is a non-deterministic path to achieving a goal, meaning you're turning over the decision-making process or breaking down the problem using the AI system itself. So how do these Agentic AI systems work? Well, they plan, iterate, and coordinate with minimal human intervention. They break down problems just like humans would do. They have control loops. They analyze the problem. They create tasks to get to that end result. And they also have the ability to adjust their path because maybe something in the research they find requires it. In the end, the Agentic AI is always trying to find the answer, are we done yet? And if it isn't, we know that there's more tasks or work to be done. They need to have memory in order to understand where they've gone and where they're going. And they also have the ability to call APIs, search the web, and do a bunch of other cool, interesting things. So what's the big deal with Agentic AI? If you're talking about AI systems being able to work on problems with minimal human intervention, working towards a goal, breaking the problem down into several tasks, and also researching in order to achieve a goal, then you're talking about a huge opportunity for automation. This covers everything from automated content generation to AI systems building business processes or operationalizing tasks that need to be done. So how does this work? Prior to agentic systems, we tried to direct LLMs to do this using chain of thought. You created a chain of thought prompt in order to guide an LLM down a path with a series of steps to answer a problem. Now with the advent of Agentic AI, these AI systems are able to break down the tasks into subtasks themselves and iterate on those tasks in order to get to their goal. So what does this all mean? For the first time, AI systems are truly doing dynamic decision-making. They're deciding in real time how to tackle a problem, how to research a problem, and what the final answer for the prompt or the question is. And this is super beyond powerful. Probably the best example of this process is using ChatGPT's research mode. If you haven't tried it, I would highly recommend looking at it. So let's talk about agentic systems solving problems. So there's a really cool framework out there called CrewAI. It's an open source Python framework. It works via role and task-based orchestration, where you have a series of predefined agents working in teams, hence the name Crew. Each agent has a role where they offer up expertise in a particular area, and it's the collective effort of this crew working towards providing answer to its prompt. The agents can delegate work to one another in order to reach their stated objective. CrewAI also allows you to access external tools. This is useful if you're trying to do things like hit an API, access the internet to do research, and so on. The big takeaway is CrewAI is a very opinionated framework on how you do agentic AI. The really cool thing is it's easy to use, it's straightforward, and you can pick this up very, very quickly. So having said that, let's go ahead and take a look at our first demo. So this is the simplest case for a CrewAI-based agentic system. The way CrewAI works, you have multiple agents, each agent's assigned a role, and they work collectively to break down tasks in order to solve the collective problem. In this minimalistic CrewAI example, you have two agents, you have a researcher and a writer, and the two tasks that we have are research latest trends in AI for this particular year and distill the findings into crisp bullet points. Then there's a second task, which is use the research data, which we used in the previous step, and create a 3-paragraph summary suitable for a technical blog. You can see this right task is dependent on the context of this research task, which is where we're finding the information in order to write and compose a blog post. Here you have your crew container, which is named AI Research Report Crew, which assembles the agents and the tasks they need to accomplish in order to meet their stated objective. Finally, we have our main function, which orchestrates this entire workflow. So let's go ahead and take a look and run this application. Here we've kicked off the process, and currently the task being worked on is the research phase, which is research the latest trends in AI. Based on the findings, we have our writer task, which is create the blog post. And finally, here's our 3-paragraph blog post, which contains all of the research regarding AI within the past year. So now that we've talked about CrewAI, let's talk about how we can extend this functionality using MCP, or Model Context Protocol. For those that aren't familiar with MCP, or Model Context Protocol, MCP is a protocol definition that describes how to connect external tools to existing agents and LLMs. What it buys you is that you're able to access new sources of data or controls that might otherwise be difficult to hook up, because each API offers its own opinion-weighted way to talk to a backend system. Previous to MCP, if you wanted to connect your LLM or agent to Slack, for example, you would need to consume an API or SDK specific implementation, where you can then read or publish Slack messages. Changes to those APIs and SDKs meant your entire agent needed to be updated. So the way this protocol works is that your agent or LLM uses an MCP client to speak to an MCP server or endpoint. That interface or protocol is the same between all MCP clients and servers. What's behind that MCP server could be a database. It could be access to Slack APIs. It could be another LLM. It's a framework for advertising an MCP's server capabilities and then establishing a handshake for how you pass off the capabilities back to the LLM or agent. So the TLDR is that MCP is a unified protocol designed to abstract away specific details of how the underlying system functions, its capabilities, and the work that it provides. Now, I love this picture because conceptually, at a high level, this is a great way of thinking about MCP servers and clients. The way to think about Model Context Protocol is it's effectively a USB hub. It allows you to connect various different capabilities into your agentic system or your LLM based on the kinds of needs you have to solving the problem. Since the protocol is the same, you can hook up anything, whether it's Slack, Google Drive, or local file sources. Think about MCP as a USB hub to hook the things that you're interested in up to your LLM or your agent. So what this looks like more concretely is captured in this very simple picture. What this looks like on the left-hand side before you used MCP, if you had an LLM and wanted to talk to Slack, Google Drive, or GitHub, you would need to implement very specific APIs in your agent in order to access those systems. This would be basically grabbing the GitHub, Google Drive SDK, and then having those implementation details direct in your code using client-side function calling. After MCP, you can access multiple servers using a single unified protocol that defines how MCP server and the client interact with each other. Then, based on the capabilities of your endpoint, the client connects to the server, and behind your MCP service is where you have that unique API that you're making available to your LLM or agent. So again, this is very cool because it doesn't put an SDK or API dependencies in your agent or LLM. So what does MCP give us? It provides us a unified way of adding tooling for all types of tools. Think of it as the everything toolkit. We're able to provide new function capabilities via MCP servers or endpoints. So why is that important to us? It's important now because the agents and LLMs don't need to know everything. This is a very interesting concept because we first started with LLMs, where you needed hundreds of billions of parameters for these AI systems to be trained on. The effectiveness of the response was provided based on the information it was trained on. Here, for the first time, you don't need to know everything, and these LLMs can call out to MCP servers in order to hook up data sources of knowledge for a particular subject matter. If we're talking about these agents augmenting their capabilities using MCP servers with the ability to make their own decisions, you're describing specialized LLMs or RAG agents that are subject matter experts in a particular field, providing its knowledge to these higher level agentic systems. Since these areas of knowledge are broken up among many subject matter experts in agent form, now you're truly talking about a Swiss Army knife of knowledge or capabilities, and all that's required is to hook them up using MCP. So instead of just talking about it, I thought I'd show you a very simple example of what MCP can do via a demo. Let's go ahead and take a look. So for this demo, we're going to use CrewAI and a CrewAI MCP adapter, which allows you to take an LLM that's a part of a crew and expose MCP tools and functionality to that particular agent. What's really great about this is you can have a general purpose agent that's not designed specifically to address any single task. And in this particular example here, You can see that we're using an MCP adapter in order to hook our agent up to PubMed Access, which is an online repository of medical publications, journals, and citations. This way, you can provide an agent the functionality of being able to access external information so that it can research any generic topic. And we have a second agent, a part of our crew. Based on the information the first researcher agent finds, our writer agent is going to compose a concise report based on provided research. And just like in our previous demo, our first task is a research task, but we're going to use the PubMed tools via an MCP endpoint in order to collect all of the research that we need in order to compose our medical-based report. Again, the task states that we're going to create 3 coherent paragraphs for a technical blog post. Here we're assembling our crew, which is composed of our researcher and writer agent, and the 2 tasks, which is composed of a research task and the final task to write the blog post. And within our main function here, you can see we have an MCP adapt and our CrewAI adapter, which allows us to expose our MCP endpoint to the agents within our crew. Let's go ahead and give this demo a try. What's really interesting to see here is that you can see our research agent invoking the PubMed tools in order to research a particular topic within the PubMed repository. Here you can see HTTP GET requests in order to access NIH documentation and studies. Here you can see the research agent requires even more research. So again, it's going out and doing an HTTP GET for a couple of NIH articles. After all that information is obtained, you can see that our research agent is able to complete its task based on the information available. And our writer agent is able to take the composed research and formulate a final blog post, which you can see right here. Now that we have an understanding of what CrewAI is, I thought it'd be interesting to compare and contrast the Agent2Agent protocol and how it differs between CrewAI. So for those that aren't familiar with what Agent2Agent protocol is, it was developed by Google and is now a part of the Linux Foundation. It's a protocol for multi-agent interoperability, where these agents aren't self-contained within a single process. Rather, they're distributed agents that communicate via HTTPS, and these agents can communicate with one another and delegate subtasks to each other. Google has this functionality implemented in their agent development toolkit, but if you aren't looking to do anything Google, there's an agnostic implementation for Agent2Agent protocol in GitHub, where you can hook up multiple agents in a non-Google and non-Gemini fashion with one another. So a brief recap. Agent2Agent protocol allows multiple agents to talk with each other, and MCP allows a single agent to access multiple tools in order to complete a request. Since these are orthogonal to each other, you can use Agent2Agent and MCP together in your solution, which means that you can do really cool and interesting things, like in this architecture diagram right here. Here you have 2 distributed agents. One could be a given cloud provider, and the other could be on-prem. Each agent might enlist MCP in order to hook up external APIs, SaaS platforms, and etc., necessary for your agent to provide its specialization. In this particular example, you have 2 agents that are able to talk to each other over the Agent2Agent protocol in order to work on a particular problem together. One agent might be specifically geared towards providing an area of expertise, and the system might pass off that task to that agent, which is best suited to do that work. So let's now discuss the differences between Agent2Agent protocol and CrewAI. Like we discussed prior, CrewAI is a very opinionated framework. It's role and task-based, but more importantly, the agents and tasks are self-contained in one isolated system. Each agent provides their area of expertise, but they are agents that exist in the context of a single crew. You're able to use MCP in order to access other tools or external resources or capabilities. The main thing to note is that CrewAI has a very predefined workflow at the heart of its framework, geared towards solving a single objective. A concrete example of this is if the crew's job is to solve a problem related in a medical context, like understanding and answering questions about medical conditions and diseases. You wouldn't ask this particular crew about puppies or rainbows because that's not what that crew's function is all about. So you can see the limitation that the particular crew is working towards in this predefined workflow. It's very difficult to scale out other areas of expertise. This is where Agent2Agent protocol steps in. Agent2Agent protocol can be a collection of externally available distributed agents where if a particular conversation about rainbows and puppies came about, where it required medical or veterinary knowledge, a system using agent-to-agent would be better suited to handle this based on the agent's area of expertise. So this is a very simple agent-agent architecture. We have 3 agents coordinating with one another in order to provide a response to a client. This is the first demo that I'm going to show you, where you have 2 agents providing very specific capabilities. One agent can summarize and distill information down. A second agent, that is a question and answer agent, is hooked up to PubMed, which is an online repository for medical text journals and information. Then finally, you have a coordinating agent that understands when it needs to enlist the capabilities of summarization and asking medical advice. It'll pass that information on to one of these other agents. So without any further ado, here's a very simple implementation for agent-to-agent protocol. So we have 4 console windows, 3 windows for our 3 agents, and then our last console window for our client. Again, this solution architecture is composed of 3 agents: the question and answer agent, the summarization agent, and finally the coordinating agent. So let's go ahead and start the question and answer agent, which effectively allows us to do research in order to obtain information required by the other agents. Next, we're going to go ahead and start the summarization agent. This summarization agent will take all of the information provided and provide us a concise report or summary about what was discussed in this particular task. And finally, our third agent, which is just our coordinating agent, which is going to coordinate all of the effort between the summarization agent and the Q&A agent. So for our client application, we're going to ask our coordinating agent, which encompasses our summarization agent and our Q&A agent, about NASA's Artemis program. Here you can see a bunch of context related to our query, and we're going to also ask, which is where the question and answer agent comes in, what is one major engineering challenge not mentioned in the text provided? And finally, we're going to generate a report based on the information that we're providing our agent. Let's go ahead and give it a try. Here you can see the coordinating agent receives the request, which is then calling out to the Q&A agent in order to obtain an answer about the question that we're posing in the context provided. Finally, we can see a summarization based on the query that we've created, and we can see that we have the answer that we're interested in. One major engineering challenge not mentioned in the text is the development of reliable propulsion systems for deep space travel. So now that we've seen the demo, let's bring this all together. So we talked about CrewAI, we talked about MCP, we've talked about agent-to-agent protocol. So why did I bring agent-to-agent protocol and MCP into this discussion? It turns out that you can use CrewAI in order to implement one of your subject matter experts. Since CrewAI offers a very prescribed and simple way to implement an AI agent geared towards solving a single task, this works well with using CrewAI to implement one of these agents. So for this particular demo, I'm expanding the previous demo to include a third subject matter expert. And in this case, it's an image creation agent. That image creation agent is implemented using CrewAI. And what this image creation agent does is, based on the context of the conversation, it will create a picture or an illustration based on the topic of what's being discussed. So without any further ado, let's go ahead and take a look at the demo. First, we're going to start our image creation agent. Next, we'll start the question and answer agent, followed by our summarization agent, and finally our coordination agent. Finally, for our client, we'll continue with our previous example using the information regarding NASA's Artemis program, which was used to establish a sustainable human presence on the moon. What's changed in this particular demo is that we're going to ask our coordination agent to create an illustration regarding the context of the conversation. Let's go ahead and run the demo. And there you have it. We have a summarization of the text provided. We filled in the gaps in our research using the question and answer agent. And finally, we created an image using the OpenAI image generation model. So the big takeaway here, there are great use cases for CrewAI. It's very easy to prototype. It implements a standalone agentic system. You can enlist multiple agents in your crew in order to build applications very, very quickly. These agents are contained in a standalone or single process. You can share the resources much easier amongst agents because they exist within that one process. And you can do that all using code. As we've also shown, you can use CrewAI to leverage MCP endpoints, so this is a huge plus. Model Context Protocol. Think of it as a toolkit of functionality. And that functionality is anything your heart desires, as long as there's an MCP protocol interface. This allows you to hook up any type of external functionality to your LLM or agent. Finally, Agent-to-Agent Protocol is best suited for distributed agents collaborating and working together where the collaboration is potentially non-deterministic. That's the big difference between CrewAI and Agent-to-Agent Protocol. CrewAI has predefined tasks that need to be tackled with agents contained within, whereas Agent-to-Agent Protocol breaks a particular problem down, enlisting the help of other agents in a distributed and non-deterministic fashion.